point in the introduction, somebody asked you to silence your cell phones. Adam said no outbursts tonight, so I would allow some outbursts, and that's if it's somebody keeping up with the Ranger game. So, and I'd also welcome in between speakers an update on the Ranger game too. So I think we'd probably all much rather be watching the Rangers than here this evening, but this is important for you. Understand that, and my goal is to help give you some insight on our business, how we go about our business, as Adam said, how we make some of our decisions, and just the general process overall. I'll touch a little bit on how the regulatory group works with us, or we work with them, how we meet their regulations, and so forth. So let me see, there it is. So first, I'll start my presentation, tell you a little bit about Devon, if you don't know who we are, what we do, where we're located. Then I'll go into the process itself, the steps we go through to drill, complete, and produce a well. And then I'll get a little bit more in depth on some of the other parts, water, some emissions, some of the things, fracturing, some of the things I feel like you probably want to hear, and hopefully my goal is to answer some of your questions. And then at the end, we're more than happy to answer the questions you have for us. So start out with Devon and our history. Devon was a private company in 1971. Father, son, and maybe one or two other guys got together and created Devon. In '88, they became a public company. Now we're on the New York Stock Exchange. We're at 5,000 employees. So that's just an amazing story in itself, and how a couple of folks could grow into 5,000 employees. Devon is an independent producer. Now I say that in relation to a major producer. Your Exxons, your Shells, your Texacos are your majors, and the difference between an independent and a major is a major has basically retail sales. Devon being an independent, we produce oil and gas. We do not have retail sales. We do not have gas stations. We do not sell directly to the end user of somebody's home. So no refining or service stations. All right, unlocking the potential of the shale. I'm sure many of you have probably seen this map before. It's very, can y'all see that arrow up there? All right, very good, very good. In the blue is the Barnett Shale, encompasses about 20 counties. Play-wide production today is about 5 billion cubic feet of gas a day, and that's coming from right now about 15,000 wells. The interesting thing, well, I'll talk about it a little bit here. Devon entered the play in 2002. And I can, at this point, give you a little bit more background into myself. As Adam said, I am the completion manager. I work out of the Bridgeport office, just about 45 minutes west of Denton. I was with the Mitchell Group. Went to work for Mitchell in 1983, straight out of college. And Mitchell had drilled the first Barnett Shale well in 1981. In 1982, they drilled like 4. In 1983, they drilled like 6. And we'll talk a little bit more about it in a little bit. This is a core of the Barnett. These will be up here afterwards. I'll be here. I'll be glad to answer questions afterwards. But if you look at this and just the fact there's natural gas in this rock, the natural gas is produced out of this rock, is amazing in itself. I'm a petroleum engineer by training. This is stuff they taught us in petroleum engineering you don't get gas out of. This is not considered a reservoir rock versus this rock. This would be considered, and I'll get a little bit more into that. But Mitchell had unlocked the Barnett to a point of getting just vertical wells and some of the fracture stimulation questions. All the wells beginning back in 1981 were fractured. What Devon brought to the play when they bought Mitchell, one, they saw the potential of the Barnett. I don't think anybody envisioned the potential of the Barnett as where it is today and what it means to the industry and to the nation for the amount of energy we're producing. And what I'm referring to there is here is where we pioneered how to produce that gas. Now it's being done in shales in the Marcellus in Louisiana. Well, let me back up and get that straight. Marcellus in the Northeast, Pennsylvania, New York, Haynesville in Louisiana, Eagleford, South Texas, North Dakota, just all across the nation. So it's a huge source of energy for us as a nation. As I said, technology, light sand frac, horizontal drilling. This is a good, basically a cartoon, so to speak. Where'd that mouse go? There it is. In the early years, if you can see this well right here, this is a sandstone. This would be what we call a sandstone here. This is your Barnett Shale. We knew the Barnett Shale was there. This represents a rock like this. George Mitchell started drilling for gas from that rock in the early 1950s in Wise County. All right, I got to keep up that booger somewhere. In the early 80s, he started drilling vertical wells, which is depicted over here on my left. That'd be your left also, that's good, and completing those. And then Devon entered the play in 2002 and started drilling the horizontal wells. So what's significant about this is the gas that was produced from this, what we'd call a conglomerate rock, actually originated in the Barnett. The Barnett is known as a source rock. This rock is 330 million years old. That's where everything was deposited. It decayed over years. It was compacted, pressure and heat, turned into a hydrocarbon. The hydrocarbon leaked up through cracks or whatever and caught in traps in the shallower zones, and now we've figured out how to produce the Barnett out of the shale. This shows, here's Denton right here, Denton County, Wise County, Tarrant, Parker, obviously. What you see in yellow are the leases that belong to Devon. This is where we are producing gas and where we are doing our drilling. So you can tell we're heavy into Denton, and that's why we appreciate the opportunity to be here tonight to be a part of Denton, hopefully, in their redoing of their ordinance. Overall net acreage, a lot of this is not real important, but this just gives you a perspective of the size. One thing I will point out, net risked resource, 18 trillion cubic feet equivalent of gas is what we're saying we have available, Devon has available in our acreage. From the start in 1981 till today, 30 years ago, we've got about 4,500 wells producing. And just this last month, we hit 3 TCF. So Adam and I was talking earlier, what's the potential, what's going to happen beyond here? We've still got 15 TCF to produce. Right now at our rate of 1.2 BCF a day, if I can do that real quick in my head, it takes about 2.5 years for us to produce a TCF. The amazing thing about that 18 TCF number is probably still growing, and it grows with our evolution of technology and how we can produce this gas. All right, here's what I feel is some of the meat of what we want to talk about, and that's the life cycle of the Barnett Shale well itself. Some of the early decisions are in the taking of leases, deciding where we're going to lease acreage. And a lease is a contract between us, Devon the producer, and the mineral owner. Someone else owns the mineral. When Devon takes a lease, we are still not the owner of those minerals. We are the leasee, and our agreement says we will produce your minerals, and for that we'll give you a portion of the revenue off that. We'll take the rest of that process and sell the gas. We bear all the cost, all the expense. I'm sure you've probably heard a lot about leasing. Now, there's a lot that goes into deciding where you want to lease. One, you don't want to take leases that aren't going to be productive. So you've looked at some geology, you've looked at some seismic if it's available. Maybe you've looked at offset production if it's a area that's been producing. take that lease, and then now you do some further evaluation, make a plan on how we can most efficiently produce the gas out of the rock. Our goal is to drill as few wells as necessary to get as much gas out of the rock as we possibly can. So that's to be efficient. Once we've decided where we're going to drill those wells, then we start our permitting process. It kind of starts down here at the bottom. It all works together. We stake that well on that property. We figure out that's where it's going to be. We make sure it's a workable location for us from a geologic standpoint, from a surface standpoint. We also work with that surface owner, try to make it workable for them as best we can. And if that's doable, and then we start our permitting process, and that involves Texas Railroad Commission primarily. It previously involved the Texas Commission on Environmental Quality, and where our involvement was there was in where we had to protect the groundwater. I think that has all now been pushed over into the Railroad Commission, but every well we have to submit where we are, and they tell us the depth of the groundwater that we have to protect. And I'll get a little bit more into groundwater protection in just a minute. Once permits are approved, other permits, if we're in the city limits of Denton, if we're in the ETJ of Denton, okay, now we've got to work through their process as well and get their authority. Other things that we might be faced with, EPA, Federal Aviation Commission, or Federal Aviation Association. I think that's right. I may be missing that. Anyway, if you're near an airport, okay, airports don't like structures sitting 150 foot in the air that weren't there the day before and then show up the next day. So there's areas, if you're within 2 miles of the end of the runway, 5 miles of the end of the runway, there's regulations there. Corps of Engineers, if you're working around Corps property, Corps Lake, EPA, we have restrictions there around flood zones, flood areas. So there's a lot of things that have to be done to make sure we've got the ability to drill that well. Next step obviously is drilling, setting surface casing. What I brought over here to the right is on the outside, the biggest pipe, that is a piece of surface casing. Surface casing is what we set in place to protect groundwater. That happens generally within the first 12 hours of once you start drilling the well. And setting that in place is just like if you were to go out and drill yourself a water well. It's the same process. You take a drilling rig, obviously with a water well, if you're just drilling a water well, it's a much smaller rig. We're going to drill 2 miles deep, so we've got a bigger rig. But we're going to drill to 1,000 feet, 800 feet, whatever's been dictated to us by the Railroad Commission at this point. We'll do that first day. We'll run steel pipe all the way in, and then we'll place cement all the way to the surface. The pipe, the cement qualifications, how long it has to be there and all of those are regulated by the Railroad Commission, and we also have to give them notification prior to setting that surface casing. So a well within its first 24 hours has the groundwater protected, sealed off, and we've got to give time for that cement to set up, and then we'll go back to drilling. You'll drill the Barnett, you'll turn it sideways. We go generally about 6,500 feet, depending on where you are, straight down, make a turn, and today, some of the evolution of technology, we're able to drill horizontally 6,000, 7,000 feet. When we first started drilling horizontally, we were looking at 1,500 feet, 2,500 feet. The great part about that, if we can go 7,000 feet, we've just eliminated 2 other wells. If I could only do 2,500 feet before, to get that 7,000 feet, 7,500 feet, I'd have to put 3 wells in. But now with technology, I can go 7,000 feet, and I've taken up the place of 3 wells with a single well. And that doesn't even count if you go back to drilling vertical wells. I venture to guess, if you were going to drill vertical wells to recover the gas that a single well with 7,000 feet, you've probably eliminated 15 to 20 wells possibly. So the industry, with the evolution of technology, is doing what it can to reduce our impact on the surface. Again, once we get that well drilled, we'll set another string of casing. And that's that middle pipe that that you can see over here. They've got windows cut in them so you can give you just a good idea of how they fit in together and the thickness of the steel. That is also concreted in place. The cement we place, where we place that cement again is dictated by the regulators. Hydraulic fracturing. Drilling rig moves off. Now it's time to produce this rock. This rock would not produce without hydraulic fracturing. Fracturing, and actually this rock, even in the 50s, was all fractured. We used hydraulic fracturing in the 50s to get the gas and oil out of this rock as well. I'll get a little bit more in depth into the fracturing in a little bit, but it's basically the pumping of water and sand to put cracks in the rock to allow that gas to escape. The water required is about 4 million gallons. That's the drilling portion of it took about 500, 600,000 gallons. 4 million gallons is what we use in the fracture stimulation. That changes with the length of lateral. Obviously, a longer lateral is going to take some more water than a shorter lateral is. And then once the well is fracture stimulated, we've got some post operations, some final cleanup of the well bore, and then we run that final string of pipe. The smallest diameter pipe you see over here to the right is the tubing string. And if I go in sizes, the bottom pipe is 9 5/8 in diameter, the middle is 5 1/2 inches, and that last string of pipe is 2 3/8 inches. And then behind that is just a model of a wellhead. All of that ties together at the surface, and we can monitor anything in this annulus area between these and this annulus here and between here. So that being said, we can monitor that everything is intact, and I'll talk a little bit about that. Again, that's how important that is with the fracture stimulation side of things. Production, this is a picture of a Christmas tree. Longest phase of the life of a well. First well was drilled in '81. It's still producing today. It's 30 years old. We re-fracture stimulated that well about 3 years ago, made it as good as new, and it's going on. That was a vertical well. Horizontals may be a little bit different, but these wells are going to be here 50 years plus. So that's your longest phase. That's our biggest employment center within Devon. We've got probably, to check our 4,500 wells, we've got 150 folks that it's their daily routine to go by and check these wells. And we also have some of the other technology, SCADA ability. What's happening on that individual well is monitored 24 hours a day. There's alarm systems, there's things that we can keep up, and that's just getting bigger and better every day as we speak. Midstream operations, obviously these wells are producing gas. The way you get gas from out of that pipe, once the gas enters the pipe at 7,000 feet below the ground, it stays in pipe until it gets to its end user. And that's done with pipelines, and that's what we've shown here, the midstream operation. There's a gathering system out there that collects the gas from the wells. That pipe comes together into bigger pipe, we call them laterals, and they maybe end up in a treating facility. They may end up in a processing facility. We have a large facility west of Bridgeport that removes the propanes, the butanes, some of the heaviers. This side of Denton, we don't have as much of the propanes and the butanes, so we don't process that to recover those. We do process it to remove the water before it goes to an end user, so you can use it safely in your home. That pretty much covers natural gas, the midstream side of operations. Okay, now I want to get into a little bit more in depth on hydraulic fracturing. This may be a little bit hard to see, and this is one of the most important things about hydraulic fracturing is basically the construction of the wellbore. I think it's a known fact that hydraulic fracturing of rock itself has not contaminated groundwater. What you do have to be mindful of is proper well construction, and that's what's in place here. This is a string of pipe, this little short one, that is called conductor casing. That's placed early to help us drill that surface hole. It may only be 80 feet in depth. And then here is your surface casing. That's going to be 800 feet to 1,000 feet. And then finally, you've got your production casing and you've got your tubing here. When we fracture stimulate a well, this is in place, protecting groundwater. This is in place. This piece of pipe is not. And the pumping of the water in the sand is actually pumped down through the 5.5 casing. The pressures between these two, we monitor that, and that's through this valve right here. That's what's being shown on the side. And it's the surface casing valve. That valve is left open, so instantaneously, if there happened to be a failure within this pipe, we're going to know immediately out here, so we don't cause any failure in the surface casing. So that's standard practice within the industry and how important that is. Railroad Commission has rules for the life of that well. We have to monitor that surface casing annulus for the life of the well. So we know if there's a problem there, then we can address it. Fracturing fluid. The nice thing about the shales is we're basically able to pump just fresh water and sand. And the fracturing process, and what I find is people don't understand or don't realize, the fracturing process is a mechanical process. It's not a chemical process. And the mechanics of it are pumping water at high enough pressure to overcome the stresses within the rock and then to be able to break that rock apart. The sand is placed to get in the cracks and to help hold the cracks open. And what you'll notice about, these are called cores, which are drilled with a special bit, just cuts around the outside, was able to grab that rock and bring it up. And if you come up and look at this one's got a scribe in it they knew exactly which direction this rock was sitting in the earth. It's been cut. This one has had some smaller cores cut out of it. And all of that is done by the geophysics people. They studied the rock. They determined the stresses within the rock. So we know at what pressure we can expect this rock to crack. And the beauty of it is we've got rocks above us that have higher stresses within it than what we have here. And the same generally goes true for what's below us. The only way we can be efficient and be able to recover gas is to keep that fracture stimulation within the Barnett Shale. I talked about the sand. It's a very fine-grained sand, very uniform sand that's mined in many places. And then the additives, I talked about it being a mechanical process. The chemicals that are involved in this are there to treat the water. It's there to kill the bacteria. Bacteria can create some corrosive things in the pipe, so we want to kill the bacteria. The other thing is a friction reducer. We're in the fracture process, you're pumping 80 barrels a minute. There's 42 gallons in a barrel, so you're pumping greater than 3,000 gallons a minute. Your water hose probably puts out about 4 gallons a minute. So that creates a lot of friction. We use a friction reducer that helps reduce the friction, helps lessen the amount of horsepower needed to do that. This slide actually says gelling agents carry the sand. Conventional wisdom, what I was taught in school, when you want to pump a fracture stimulation, you want to place sand in the cracks. And to get sand to stay suspended, you had to create some viscosity in the fluid. And that's where the gelling agents, basically to look like Jell-O. What's nice about the Barnett and these shales, you don't need the gelling agents to do that. So bottom line, what I'm telling you is the chemicals are minimal. The chemicals are there to treat the water and not really treat the formation. The other thing this is a website, Frac Focus. This is where companies such as Mitchell are voluntarily posting their chemicals used in frac jobs. Railroad Commission is working on some regulations on reporting of chemicals. I'm sure John may touch on that in a little bit, but we're supportive of doing those. Obviously, there's companies that sell these chemicals. They want to keep their secrets to themselves, but there is going to be some reporting of chemicals. Probably running close to my time. I'll run through this pretty quick. Water use in the Barnett. This is just a slide showing the amount, and this was from 2008. That was peak of activity. Even back in 2008, just total water use in the Barnett, the industry, the oil and gas industry, was only using about 3% of the water being used. Two kinds of water in the Barnett: flowback water. Flowback water is another term for the water we push into the Barnett to use to frack it, to crack the rock. We want to produce that water back out. That water's in the way of the gas, so we want to produce it back. So that's how it got its name, flowback water. So as soon as we finish fracking, we'll flow it back. You have other water that can be produced, and that usually comes from the Ellenberger, which is directly below the Barnett, starting at about 8,000 feet, going to 11,000, 12,000 feet. It is full of water, salt water. As you can see here, chloride content's generally 100,000 to 120,000 parts per million. Well, one of the other great things that we found early on is we could pump our water back into the Ellenberger. So the produced water we're making is going back into the Ellenberger, 8,000 to 10,000 feet below the surface. Now, what Devon has done, starting back in 2000, we started looking at it in 2004. We actually started recycling water in 2005, and primarily focusing on the flowback water. That flowback water, when it comes back, it's still fairly fresh. The longer it stays in formation, the more of the chlorides and the salts it's going to pick up, but we're able to treat and recycle that. That's done with a mobile heated distillation system. It's really a pretty simple process. You boil the water, you create steam, you recompress the steam into distilled water. So we're actually creating distilled water. And since we started this, we've created 11.5 million barrels of distilled water. That water is then taken to another frac job and used again. So that has been huge. That is something that was not regularly done within the industry. You get to other plays like the Marcellus, they don't have an Ellenberger. They don't have the ability to dispose of water as easily as we do. So this technology, the fact that we pioneered it here, we've learned about it here, is being applied in other places. We've also taken the opportunity to test other systems to try to find that best mousetrap. I mean, it's basically a trial and error period, and it took Mitchell/Devon basically 17 years to figure out how to economically produce the Barnett. Emission reduction. Devon has been a member of the EPA's STAR program, and STAR program is just a voluntary program in which we commit to reduce our emissions as best we can, and we report our reductions. We do that through green completions. I'll talk about that a little bit more in a minute. Low bleed pneumatics, plunger lifts, vapor recovery units, and such. And we've been recognized multiple times there. Rookie of the Year in 2004, Partner Year in 2005, and then Continuing Excellence in 2008 and 2010. I talked about flowback water. We want to get that water back out of the ground. That's a process of flowing that well back. Well, you're producing that water back. You start producing some gas. A green completion is capturing that gas when we flow it back and putting it in a pipeline. It makes perfectly good sense. And we've been able to exercise that ability since 2004 here in the Barnett. And what's allowed us to do that is the fact the only way you can do that is if you've got a pipeline infrastructure in place. You've got to have a pipeline on the location. But what you see in the pictures are some of the rental equipment that we use. That flowback comes up, we have to separate the water out. The water, in this case, in Denton, goes to a recycle facility. The gas stays in the pipe, goes in the pipeline. If you didn't have the pipeline there, then that gas will be vented to the atmosphere, which is a regulated process, and we're allowed to do it for the completion of the well because it's necessary to get the water out to help clean it up. Tank emissions, and I throw this slide in there to talk about vapor recovery units. This is depicting over here the mix. This is the flow coming from your well into a separator. What's in the gray is your water. Your gas is on top. In this separator, the two phases separate out. Liquid in the bottom, gas on the top. The gas goes out and goes into a pipeline, and the water goes into a tank. Now, what you can have, if you had some heavies, you can have some entrained vapors escape from this water into this tank. This is not a pressurized tank. What you have here, this mix is coming into this separator, probably about 300 pounds of pressure. It leaves there at about 30 pounds and dumps into a tank that's basically at atmospheric pressure. So you can have some release of vapors there. If you have a lot of vapors, then you have the opportunity to set a vapor recovery unit, and that's just basically a small compressor that will collect those vapors off that tank and put it back into the pipeline. And here's a depiction of that. Basically the same process we had here. Here's your well, flow into the separator, your liquids going in the tank. You've got a large amount of vapors coming here that are being collected in the vapor recovery unit and placed back in the pipeline. The key point here is vapor recovery units are the thing that's been used on every well. Every well is different, and it depends a lot on the composition of the gas and the fluids you're producing. So if you're producing condensate, yes, you're probably going to have enough vapor to set a vapor recovery unit. And it's in our best interest. We want to capture that gas. We want to capture those vapors because that helps with the economics of that well. So that's pretty quick. I think hopefully I'm not too far over my time. I'll leave you with some websites here for some additional information. If you feel free to jot those down. And Adam, you want me to turn it over to you?